Okay, we're getting close to the end of this section on trigonometry, and I'm sure you're not going to shed a tear when that happens. It's been a long section. We're finishing off now with what's called the general solution to trig equations. Now we've discussed in solving trig equations that there are an infinite number of solutions, and so to counter that, we're often asked to represent our solutions in a certain domain. Right? So we've had a bit of a go at that and what have you. General solution is finding what all the solutions are. Let me sort of explain, or a way of representing all the solutions. So obviously there's an infinite number of solutions. We're going to try and represent that algebraically. Okay, so let's have a go at what I'm talking about. Cos x equals a half. So let's proceed as we would normally with this question and find, okay, a half, that looks like one of those little triangles, isn't it? It's one of those exact values. 1 there, 2 there, root 3 there. Cos being a half is that angle in there, isn't it? Adjacent over hypotenuse. That angle is pi on 3. We're going to go with general solutions. We have to stick with radians. That's the convention. So pi over 3 here, not 60. Right, so x equals pi over 3. That's a solution. But that's just one of them, isn't it? Let's go and have a look at where the other solutions are. It's positive, so the other solution's in this quadrant. Now, I'm going to write this as I'm not going to give it its the single solution. I'm going to write it as 2 pi minus pi on 3, if you know what I mean. So I'm representing this solution here, where I've got pi on 3 in there, if you get my drift, as 2 pi minus pi on 3, rather than simplifying that to 5 pi on 3. I'm just going to leave it like that, and you'll see why hopefully in a moment. Now, if we keep going, because that's great, but now we can go around again, can't we? So now we add 2 pi to this, so that's 2 pi plus pi on 3. And we add 2 pi to this. Well, actually, yeah, so we add 2 pi to that, we get 4 pi minus pi on 3. And then we just keep going, 4 pi plus pi on 3. And what we're going to do is we're going to pick up what the pattern is, and there definitely is a pattern here. We're going with what's happening here. Well, we're going with every second pi, aren't we? With even pies. This will be 6 pi plus pi on 3, and then we're going plus minus pi on 3. So the way to represent, and there is just a sort of a standardized way of doing this for each of our cos, sine, and tan, but it's nice to have a look at how it develops. We can represent this as n pi, or actually not n pi, 2n pi. That's the best way of representing an even number, because then n, I'll go through in a moment how that's the case, plus or minus pi on 3. Okay, so let's just check that this works. For n equals 0, we get, this is 0, so we just get plus or minus pi on 3. So that covers that solution. Remember, we've only gone round in the positive direction. So we're picking up the infinite solutions in a negative direction. We're picking up minus pi on 3 as well. Now, if we make n equal 1 now, n equals 1, then we get 2 pi plus or minus pi on 3. 2 pi minus, 2 pi plus. Okay, n equals 2. 2 times 2, this is an n here, 2 times 2, 4 pi plus or minus pi on 3. There's those two there. So this is what is called my general solution. This is the general solution to the equation cos x equals a half. It covers all the solutions, and as you can see, it involves a little bit of algebra bringing in an n. Okay, so that solves cos. Let's have a look at, they all look a little bit different. So let's have a look at how sine looks. So for sine, we're going to solve. So this will be b. Sine x is equal to 1 over the square root of 2. So again, we're in to one of these little triangles, and it's this 1 root 2, which is the 45er. We can't say 45, we're going to say pi on 4. So we're going pi on 4, and we're going in quadrant 1 and quadrant 2. So let's go solving. X is equal to pi on 4 in quadrant 1, and in quadrant 2, this one here, where that's pi on 4 there, we're going to call that pi minus pi on 4. And that's nice, but now we're going to go around and pick up pi on 4 in the second lap. So that's 2 pi plus pi on 4. And now pick up, so we're now here, which is now 3 pi minus pi on 4. Then we go around again and we got 4 pi plus pi on 4. And then we got 5 pi minus pi on 4. So you can see we've got some tricks to deal with here. When it's an odd number pi, it's minus pi on 4. When it's an even number pi, it's plus pi on 4. You see how that works? So we're going to try and represent that, and this is how. We're going to call this, we've got n pi, because we're picking up all the pi's, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. But the way to represent that plus minus is we can do it like this. This is a tricky little thing to do. Minus 1 to the power of n. That means when n is odd, this is a negative number. So when I've got 1 pi, this will be minus 1 to the 1, so I'll have a negative there. Put a pi on 4 there, and let's see how this works. When n equals 0, 0 pi, so 0 pi, minus 1 to 0 is just 1, so that just picks up that one. When n equals 1, we've got pi minus pi on 4, done. When n equals 2, we've got 2 pi plus 1 plus pi on 4, beautiful. N equals 3, you can see what's going on, 3 pi minus pi on 4. So this is my general solution to sine x equals 1 over root 2. Okay, we're going to have a look at a tan question. Tan x is equal to, what are we going with here? Tan x is equal to 1, let's go with 1 over root 3. Tan x equals 1 over root 3. So where are we? We're on this little 1 over root 3 is that angle there, opposite over adjacent, that is pi over 6. So we're pi over 6 and we're in quadrant 1 and quadrant 3, pi over 6 here and pi over 6 here. So x is equal to pi over 6. What's this in the third quadrant? We call it pi plus pi over 6. In the back around again, it's 2 pi plus pi on 6. Then it's 3 pi plus pi on 6. And 4 pi. So this one looks nice and easy to represent. See if you can think of it before me. Pause the screen and have a go at it, and then come back. Okay, so how did you go? I reckon it's n pi to pick up all these 2 pi, 3 pi, 4 pi, plus, it's always plus, pi over 6. Check the results of that. When n equals 0, we've got 0 plus pi on 6, it's that one. When n equals 1, we've got pi plus pi on 6. When n equals 2, we've got 2 pi plus pi on 6, and it goes like that. When these are negative, these will change around a little bit, but they'll basically, your sign is always going to have an alternating sign, just because of the nature of the quadrants that it picks up. Your cos is always going to be a plus minus because of the nature of its quadrants, 1 and 4, sorry, and tan, because they're in those opposite quadrants, will always be a plus. So, or when it's a negative, when you're solving for a negative, it'll be in these two quadrants, so that will always be a minus. So it'll be pi minus, 2 pi minus, 3 pi minus, it'll be all like that. When sine's negative, it will be in these two quadrants here, so it'll be, sorry, so that's not sine negative. When sine's negative, you'll be in these two quadrants here, so it'll be pi plus and 2 pi minus. So we'll have it'll be the odds that will be connected with the plus, and the even pi's that will be connected with the minuses, so this will have to be minus 1 to the n plus 1. That'll be for sine negative. For cos, this is cos positive. For cos negative, you'd be in these quadrants, it would be pi minus and 2 pi plus. So you would have to, it would be pi minus 2 pi, pi minus 2 pi, sorry, pi minus and pi plus, and then 3 minus and 3 pi plus, so it'd be going around in, it'd be going in 1, 3, 5 rather than 2, 4, 6, if you get what I mean. So this would have to be, this in here would have to be 2n plus 1 pi to pick up the odds. So there's a few tricks to learn there. We've just done a few examples, but we'll do more when we get in class. This is the last exercise. It's exercise 16n. I'll see you soon. Just to note that we'll do questions 1 and 2 from exercise 16n, and that's on page 486. Okay, catch you soon.